Okay, today we're doing 2.5 continuity graphically. Okay, let's get started here. First thing we're going to be doing is we're going to be doing some limits with a piecewise function. Let me get my pen here. Okay, there we go. Okay, first thing, let's do the limit as x approaches -2. Remember, with a limit, we care about where it's approaching from the left and where it's approaching from the right. We do not care about the point. So we do not care about equal signs. So let's do the limit as x approaches -2. Remember, from the left. Okay, here's -2. This one right here approaches from the left. So we're going to have to use this function. And does it also approach from the right? No. So this is the one that uses the right-hand side. Remember, we don't care about this equals sign. That has nothing to do with limits. This is the right-hand side of the function. So let's plug -2 into this and see what we get. So -2 minus 3 squared plus 6. That's going to be -25 plus 6 is going to be -19. Okay, the next one, we're going to plug in -2 into the right-hand side. It's going to be 2 times -2 plus 5. That's going to be 1. Okay, if you notice, from the left and from the right, they do not approach the same place. So we would say this limit does not exist. Okay, let's go down to this one. The limit as x approaches 4. And remember, that means from the left. We only care about from the left. So let's do 4. Okay, here's 4. This is from the right. This is from the left. So we're going to be using this function right here for the left of 4. So we're just going to plug 4 into there. 2 times 4 plus 5. That's going to give us 8 plus 5. That's going to be 13, right? So from the left, it's 13. Now notice, if you would have plugged 4 into this other one, it would have given you -4, and that would be the answer if this was a plus sign. Okay. Oh, it looks like we have that question. Sorry, I didn't even look forward. So the limit as x approaches 4 from the right. That would be this function right here, which you just plug in 4, which makes it -4. Okay, and then we got a question, the limit as x approaches 4. We got the answer already from the left and from the right. They're approaching different places, so our answer for the limit as x approaches 4 would be that it does not exist. Okay, let's do the limits as x approaches infinity and -infinity. Okay, remember, that means we're going to be looking at the end behavior. Remember, whenever you see the limit as x approaches infinity or the limit as x approaches -infinity, that's no longer the 3 rules of limits as they approach numbers. It's going to be this rule. Bobo Botsa eats DC, right? Okay, the limit as x approaches infinity. So first we're going to see which one of these we're going to be looking at if we're focusing on infinity. That would be this last one. So we're going to focus on this last one. Okay. Well, we're going to use Bobo Botsa eats DC. Well, right now we don't have a bottom, so let's give it a bottom. Okay, that's what the bottom would be if there was one, right? That's basically 1. Okay, well, our highest exponent on top is a 1. Our largest exponent on bottom is a 0. So this is bigger on top. So it's going to be Botsa. Botsa, bigger on top, slant asymptote. And we already know what this looks like, okay? If you look at a graph of -x, it looks like this. Yeah? And so your end behavior, as you go way over here to positive infinity, your end behavior is going down, right? So the answer should be -infinity. But let's see here. Bigger on top, there's a slant asymptote, which means you need to plug in our sign here, infinity, into there and see what it gives you. And if you plug in infinity, you get -infinity. So -infinity. I mean, if you can just imagine the graph, like if it's an easy graph like -x, I mean, you know what it looks like. You just look at what the end behavior looks like. If we were talking about -infinity for that exact same function, it would be positive infinity. It would be going up at the way over here on the left-hand side. Okay, let's do this one. The limit as x approaches -infinity. Okay, now we're going to be using this top one over here. Yeah? So this is the one we're going to use for x approaches -infinity. And I mean, I can already tell you what that graph looks like too, so I already know the answer. Let's do a little graph of it first of all. Okay, it's an x squared, so I know it's a parabola, and it's a negative, so I know it's a downward parabola. I don't really care about anything other than that. So it's going to look something like this. Yeah? So if you're talking about negative infinity, I mean, way over here, it's going down, so it should be negative infinity. That's just what our answer should be. But let's look at this. Let's use both sides eats DC. Okay. Well, there is no bottom, so it's automatically bigger on top, just like how it was on this one. Okay, so we need to plug in our negative infinity into here to see what it's going to be. So let's plug in negative infinity. So we got a negative, and remember, we're only plugging into the largest term. So a negative infinity of minus 3 squared. We don't worry about the plus 6. You add 6 to anything, to an infinity, it's not going to change it. So inside we got negative infinity being squared, that's positive, and then you put the negative on it, so it's negative infinity. Yeah. So, but I always first suggest, if you know what the graph looks like, draw it out. You should know what the end behavior of that graph looks like. But, I mean, that's not always the case. You might not know what the end behavior of a graph looks like. And that's when you use both sides DC. Okay, let's go to the next one. A function is continuous if it follows these 3 rules. Okay, so we're going to be talking about continuous functions. Let me give you a basic layman's term definition first, okay, before we start writing this mathematical stuff. Okay, a continuous function, continuous, in layman's terms means you can draw it, draw function without taking your pen off the paper. Okay, so here I can give you like two graphs here, and that's a really ugly y-axis. Okay, this is a function. I drew it without taking my pencil off the paper. Therefore, it is continuous. Okay, let me give you one that's not continuous. Maybe something that has a vertical asymptote. You can't draw that without taking your pencil off the paper. Maybe something that has a hole. Yeah? There's nothing there, so you have to take your pencil off the paper. Okay, so discontinuities make something not continuous. So let's look at these 3 rules. The first one is the limit as x approaches c of f of x exists. So there is a limit. Okay, so there is a limit. The next thing is there is a point. So there's a limit and there's a point. And the last thing is that that limit equals that point. Okay, remember, limits mean that you're approaching something, and here I can explain this real quick. Limits mean that you're approaching the same thing as you approach from the left and you approach from the right. Now, remember, that means you can also have a hole there and it still has a limit. Yeah? This has a limit here. F of c means that there is a point. Well, if I put a point up here, you can't draw this function without taking your pencil off the paper. But if we say the limit, as we approach something from the left and the right, is the same as the point, that means I have to put the point down here, not up on the top. And if you put the point down there, now if you were to draw this function, you can draw it all the way across without taking your pencil off the paper. So that's what this means here. Let's do some ideas here graphically. And that's just explaining that first thing that I said, draw the function without taking your pencil off the paper. And on the AP exam, you need to know these 3 rules. You must know them, okay? You must know all 3 rules. Okay, so let's do some of these on a graph. Is the function continuous at 2? Let me get a pencil here. Okay, well, first of all, you can ask yourself, can I draw this without taking my pencil off the paper? Absolutely not. It is a jump discontinuity. So I have to take my pencil off the paper. Okay, so let's talk about what it breaks. So remember, remember it has 3 rules. You must first have a limit as x approaches 2. Okay, does it? From the left it approaches 1. From the right it approaches -1. Nope. The limit does not exist. not continuous at x equals 2. Okay, let's check this one. Is the limit continuous? Well, first of all, I know I can't draw that without taking my pencil off the paper, so I know it's not continuous, but I need to tell you why. Which rule does it break? Okay, first one, the limit as x approaches 2 of our function. Let's see if it has one. From the left, it approaches 1. From the right, it approaches 1. Okay, it does have a limit. It's 1. Now let's see if it has a point. F of 2. Well, it doesn't look like I have a point anywhere on here. So there is no point. The point doesn't exist. So not continuous at x equals 2. Okay. So and then there's your answer right there. There's why it's not continuous. Here's your answer right here. There's why it's not continuous. Okay, let's go on to a couple more here. Is the function continuous at x equals 0? Okay, first thing, the limit as x approaches 0 of our function. Okay, from the left and the right, both approaching a y value of 0. We're good. F of 0, is there a point? Yeah, it looks like it's a negative half. Okay, the next thing, does the limit as x approaches 0 of our function equal f of 0? Well, no they don't. They're two different things, so they do not equal. So it's not continuous at x equals 0. And there's your reason why. The limit does not equal the point. Okay. Let's do this next one. Is the function continuous at x equals 0? Okay, the limit, it does have a limit at 0. So the limit as x approaches 0 of f of x is equal to 0. F of 0 is equal to, well, there is a point there. If there was a hole, it would show you that open circle, but it doesn't show you an open circle, so it is 0. Okay, the limit does equal it. They're the same. So we can say the limit equals the point, and all of them are equal to 0, so continuous at x equals 0. Okay guys, just real quick, they could also ask you about other points. Like let's say they asked about this point right here at 2. So is the function continuous not at x equals 0 but at x equals 2? Well, it does have a limit from the left and the right. So the limit as x approaches 2 of our function equals 1. It does have a point at 2. It's equal to 1. And those are equal to each other. The limit as x approaches 2 of our function is equal to f of 2, and they're both equal to 1. So this is continuous at x equals 2. So notice we're not always talking, this thing can be discontinuous at one point and continuous at another. That's not a problem. I might ask that on the homework. I might ask like some different points. Okay, I think I only got a few more left here for us. Okay, let's just ask the questions and we'll just figure out which one it is continuous or not continuous at. Okay, is it continuous at x equals 1? Okay, that's this line right here. It does have a limit, it does have a point, and they're equal to each other. So, oh, let me go back to that. So the answer to this one is yes. Okay, is it continuous at x equals 1? No, because the limit from the left and the right, they're not the same. So no, because the limit as x approaches 1 does not exist. Okay, this next one, same thing, the limit does not exist. The limit as x approaches 1 does not exist. Okay, this one, it does have a limit. It's negative infinity, but it does not have a point. So f of 1 does not exist. So it's not continuous. Okay guys, these are the different types of discontinuities. You have a corner, a cusp. The discontinuities, you know them all. It's the hole, the vertical asymptote, and the jump. A vertical tangent means it's up and down, and we'll talk about some of those later on in the lessons. Okay,